Yes, guys. So today I'm talking about Pappus and Guldin theorems. Now, area of surface of revolution in this case, and volume of surface of revolution given by Pappus and Guldin. First of all, I'll talk about it. What are these theorems? Who was Pappus and Guldin? Let me discuss about them. Their brief introduction, because about Pappus, what Pappus of Alexandria, nothing is known. Except his works, because initially, he was in 3rd century AD. Okay, sorry, 4th century AD. He is considered living during the period, sometimes say 311, sometimes it is 304. So in the 4th century AD. Okay, but his works are very much known, because he has written some mathematical 8 volumes which are available. Okay, and in that he was a mathematician from Greek. Okay, Greek mathematician he is known as Pappus of Alexandria. Okay, because he works as a teacher in Alexandria. It is known to what you call post researchers upon him, because Guldin then discovered, after about more than 1000 years later, he discovered his works of this Pappus of Alexandria. Okay, and then these theorems, because he elaborated those theorems given by Pappus initially, and after in 1577, when was born, 12th June 1577, Mr. Guldin was born. Okay, a mathematician or astronomer of Switzerland. He was born in Switzerland, or Swiss mathematician. So he discovered all these theorems of Pappus, and after that he added something in this. He elaborated them, these theorems, or made them known to the public, because initially they were not so much well known. So he elaborated them, and he worked with Kepler, the astronomer Kepler. Okay, because of that, this Guldin was very much famous afterwards, and these theorems are also known as Guldin theorems. Guldinus theorems, or theorems by given Guldin. So Pappus and Guldin theorem they are known as, because initially they are of Pappus of Alexandria, and these theorems have been elaborated and given some illustrative examples. Okay, with questions given by some illustrative instances, and because of that they are also known as Guldin theorems. So Pappus Guldin theorem is a proper word. I'll discuss about. Okay, let me just talk about something about Pappus and Guldin, because these are the mathematicians. Whosoever mathematician has given or some contribution to the field of mathematics, I will just mention them, their contributions to the field of mathematics, because I am also a mathematician. Just teaching students of mathematics. Okay, in different branches of mathematics, management, engineering. Okay, all kinds of competitive examinations. Okay, for GMAT, GRE, SET, CAT, MAT, every possible competitive examination in India, abroad. Okay, GMAT, GRE, SET, IELTS, TOEFL, English also I have taught. For a number of years I have taught English. Okay, so because of that, I'm just mentioning the contribution of the mathematicians, because I just give some contribution from my side to them, that they have devoted something their life, some life of theirs towards the the strengthening the field of mathematics. So they are mathematicians. So he was a mathematician and geometrician, especially Pappus of Alexandria was a geometrician, but he has given a lot of geometric theorems. Okay, so theorems in geometry which are famous, and these are the theorems known as centroid theorems, or surface and volume of revolution. Okay, or centroid theorems given by Pappus and Guldin. So Pappus and Guldin's theorems of surface and volume of revolution known as. Okay, so these theorems are written down here, first and second question. These are the two theorems. Based on them, questions are taken later in these other questions. So first theorem, which is based on volume of revolution. It says, if a closed curve revolves about a straight line in its plane, which does not intersect it, then the volume of the ring thus generated is equal to the area of the curve multiplied by the length of the path of its centroid. Now, length of the centroid, path of the centroid into area of the closed curve will give us the volume of revolution. It's a closed curve. If a closed curve revolves about a straight line in its plane which does not intersect it, means the line does not intersect the closed curve, then the volume of the ring thus generated, is equal to the area of the closed curve, into the length of the path of the centroid, This is the volume theorem. Okay, second is this: if an arc of the curve revolves about a straight line, if the arc of a curve revolves about a straight line, and this straight line doesn't intersect this arc here, the same thing is given here, and in its plane, about a straight line in its plane which does not intersect it, then the surface generated is equal to the length of the arc multiplied by the length of the centroid of this arc here. Okay, the length of the multiplied by the circumference of the circle. Circumference means length of the circle generated by the centroid of the arc. Again, the same thing is multiplied, means circumference of the circle generated by the centroid of the arc or the area. In the first, it was of area, circumference of the circle generated by the centroid of the area of the closed curve in this case, and in this case the centroid of the length of the arc, centroid of the arc. Okay, so circumference of the circle generated by the centroid of the arc in this case, second case, and the first one the centroid of the closed curve. Okay, so multiplied by the circumference of the circle generated by the centroid of the closed curve in first case. In second case, the centroid of the arc, length of the arc. This is the second. These are the two theorems given by Pappus and Guldin. They are known as Pappus and Guldin theorems. Now let me just talk about Pappus and Guldin. So Pappus of Alexandria, he is known as Pappus of Alexandria. Pappus of Alexandria, okay, was in the 4th century AD. Was in 4th century AD. 4th century AD. Okay, nothing is known about his biography. Nothing is known about his parents, about his father. Nothing is known about his biography. But from his works in mathematics, especially in geometry, one can imagine that he was working, or he was live in 311, some say in 304 or 303 or 304, okay, or in the 4th century AD. This is AD here, 311 AD, 304 AD, or in 4th century. This is 4th century, more than 300, 4th century AD. 4th century AD. So this is his time, but his works in 8 volumes of mathematics works. And he was a mathematician, or especially geometrician. He was a mathematician, a Greek mathematician. He is a Greek mathematician. He was a Greek mathematician. He was a Greek mathematician, okay, who has Greek mathematician, especially who has worked in mathematics, or contributed in mathematics, especially in geometry. Okay, so, and 8 volumes of mathematics, Volmica or Mathematica or something, okay, and especially in geometry, 8 volumes of his work in mathematics, 8 volumes of his work in mathematics. Are found to be very contributory to the methods field, very contributing to the field of mathematics, So his contribution is this, and later his work were discovered by, and they were discovered by, let me talk about Paul Guldin. Paul Guldin was, a Swiss mathematician, Switzerland mathematician, or mathematician from Switzerland. Then later, after more than 1,000 years, his works were discovered by Paul Guldin, especially the theorems on volume and the surface of revolution, about a line or in centroid, about a line in which centroid, in which centroid, these terms are known as centroid terms sometimes. Centroid is the main objective of the closed curve and the arc, length of the arc and the length of the arc. So after more than 1,000 years, so who was Paul Guldin? Let me talk about some. Paul Guldin is given. Paul Guldin was a Swiss. Paul Guldin was a Swiss mathematician and astronomer. Born on 12 June 1577. 1577. Born in Switzerland and died, and he was died on 4th November. This is 4th November 1643. Try to understand. Aged 66. He died aged 66. He died in Austria. So died in Austria and born in Switzerland. So born on 12th June 1577. And died on November 4, 1643. November 4, 16. Died on November 3. Sorry, this is number 3, not 4. I'm sorry to say, this is 3, November 3. On 3rd November 1643, or 12th June 1577, he was born. Born on 1643, aged 63, he died, and 12th June 1577, he was born. So he was a Swiss mathematician. So this is a brief history of this, but he is astronomer, and mostly he is known as contemporary of Kepler. Johannes Kepler, he is contemporary of Kepler, So astronomy he worked in. So Paul Guldin, okay, Paul Guldin was contemporary of Kepler. He worked with Kepler also. Okay, so but because of his contribution in the field of these two theorems, these two theorems of Pappus are very much known. So because of that, these theorems are now known as Pappus and Guldin theorem. Okay, so these theorems were further contributed by Paul Guldin, and because of that, these theorems are known as Pappus and Guldin theorems. So first theorem, let me talk about either the surface theorem is first one or volume theorem is first one, doesn't matter. Either write second question first or first is second, doesn't matter. Or first is volume theorem, second is the area theorem. Okay, surface of area theorem. So this is, let me talk about first one. First theorem is Pappus and Guldin theorem. So what is the Pappus and Guldin theorem? Pappus now. So these theorems are known as These theorems are known as Pappus and Guldin theorem. Pappus and Guldin or Guldinus theorem. Pappus and Guldinus theorem. Guldinus, why? Because Pappus as Guldinus theorem. And Paul Guldin is known for these theorems. Okay. Pappus and Guldinus theorems. Sorry. Pappus and Guldinus theorem. So first theorem, let me write the first theorem. First theorem is, I'm writing here, first is if a closed curve, okay, revolved about a straight line, okay, in its plane, which does not intersect it. Means this line does not intersect the closed curve, which does not intersect it. Then the volume of the curve, then the volume of the ring generated by volume of the ring, then the volume of the ring generated by the revolution, yeah. Then the volume of the ring, this is thus generated, is equal to the volume of the ring thus generated. Volume of the ring thus generated. The volume of the ring thus generated is given by, is equal to the, okay, surface area is equal to the area of the curve is equal to, first is area of the curve, closed curve in this case, area of the curve, okay, into length of the path or circumference, in this case length of the path of the centroid, path of its centroid. This we have to prove that what is this area here, this volume of revolution. This one, volume of revolution. Okay, if a closed curve will revolve about, let me take a closed curve here. Let me describe this closed curve. If I take a closed curve, let me take a closed curve here. This is a closed curve. Okay, and if I take different points here, this is x-axis, origin, y dash axis, this is origin here. Let me take 2 points here, P and Q. This is point A here. Let me take A point. This is B point here. Okay, and if I draw tangents upon these 2 points, A, and on this B point, let me take, this is B point here, tangent on the B point on this closed curve. Okay, and if I take a P point, let me take here P point here. Here it is Q point, let me take, this is Q point here. This is Q point. And if I take the length of these, perpendicular distance from the x-axis, because about the x-axis, the straight line, this closed curve will be revolved about. Then we will require, this is P point and this Q point is there. And this is Q point here. Q point length is, let me take y2, this is y2 here. And this length is, let me take y2. Height of this y coordinate, and its y coordinate is, let me take y1 of P. Okay. Now if I take centroid of this curve, and centroid of this curve, if I take, let me take here, G is the center of gravity, and if I draw perpendicular from this, this is x bar, y bar. So this height is y bar here, y coordinate. Okay, and if I take points, different points here, this is, let me take L, this is M, and here P, Q, this is suppose N, P, L, M, N, let me take P, N, height of which is, this y coordinate of this is y1, and P, Q, M, N, L, M, N, let me take P, K here, this is K here, Q, K, Q, or QK. K is looking different. Let me take some other point. R here, PQR. Okay, and this G is meeting the x-axis at the point. Let me take here PQR. S, let me take, this is S point. Okay, now this is the closed curve. This is the closed curve. What is the volume generated by this closed curve? We will talk about volume of the closed area. Closed curve. First we have to wonder what is the closed curve. Closed curve is AP, BQ, A. AP, BQ, A. This is B point here. So here closed curve, let me write here. Here, this solution we are finding out. This is the first term. Question number 1 here. We are talking about question number 1. This is statement I have written down because this is known as Pappus and Guldin theorem. Pappus and Guldin theorem, first one and second one. These two theorems I am first going to illustrate. What are these two theorems? First theorem is of closed curve. Either, okay, some writers write or some writers say that, or some people have discussed that this theorem, second number, is the first theorem of the Pappus and Guldin. Doesn't matter. Either take first as the first or second as second, that I have already described. So this closed curve, area generated by this closed curve, is revolved about this straight line. Okay, then the volume generated is equal to the volume, the surface area of this closed curve into the circumference of the circle generated by the centroid G of this closed curve. G is the centroid of this closed curve. I'll just discuss about it, how this is calculated. What is the formula? Area of the curve, closed curve in this case, and length of the path of its centroid. This is length means circumference of this closed curve, or sorry, not closed curve. Length of the path of the centroid. What does it mean? If SG is revolved about this straight line, then a circle will be generated. The length of that circle means circumference of the circle. That is, this is y bar, suppose radius. Then 2 pi into y bar is the length of this ring, which is generated, or a circle generated by SG about this line after revolving this. So the centroid is generating a circle. The length of that circle means the circumference of the circle. So circumference of the circle generated by SG after revolving this closed curve about this line, then we will get the centroid is also revolving. Okay, so that line SG, the length of the centroid from this line, will generate a circular ring, and that ring's length means circumference that is 2 pi into y bar. That we will discuss about that how this is there. Okay, so first let me discuss about that what is this. Here the closed curve, let me take here the closed curve. The closed curve is, let me take A, P, B, Q, A. Here the closed curve is APB. Then this closed curve is revolved about the line, about the straight line, about the straight line OX. Let me take OX, which does not intersect this, which does not intersect the closed curve. Means closed curve is not intersected by this line. This is clear. This closed curve is separate and this line is separate, so they are not intersecting each other. Then this volume will be what? That will be given by volume, and here I have taken AL is the abscissa, and let me take this length is C here x equal to C, let me take, and because A and B we are taking, or we can take A and small b, let me take this is small a and this is small b, and this is x equal to B, where B is greater than A. Here B is greater than A. Okay, here AL is equal to A, or this is by, these are the abscissa. Here is A, here the abscissa AB, the abscissa here AB SI double CA double SA E, abscissas AL equal to A and BM is equal to B. Let me take, so AB will take the limits from A to B of this closed curve. Then we will just discuss about. So AL here, this is abscissa, x equal to, this is x equal to A in this case. Okay, this is x equal to A. Okay, at this point x equal to A, at this point x equal to B. We are not taking x equal to A, AL equal to A, but this is x coordinate here. We are not taking this AL equal to, but x coordinate of this is AL here. So AL is, okay, AL is here, at this x coordinate is x equal to A, at AL x equal to A, and at BM, BM x equal to, this BM x equal to B. Here B is greater than A. Naturally B is greater than A because this OM is here B, OM is B, OL is X. That's coordinate of this. So between X and, this A and B limits, we have to find out what is this length here. Now if I draw perpendicular, then naturally dx is there. If I take a small elementary area and then we find out, then this is dx here, this is by coordinate, so by into dx it will be the length of the curve if I find out, and area will be by square into dx. That we will just talk about, what is the area of this curve. Okay, so that is the point, let us discuss about. Okay, now the volume, therefore the volume of the, first is, what is this volume generated by? Here the closed curve APB, okay, APB, then this closed curve is revolved about straight line OX, which does not intersect the closed curve. Then the volume generated, then the volume generated, let me find out that volume generated by this closed curve about the line OX is equal to volume generated by, or volume of the closed curve, this. Okay, we will talk about, this is volume generated by revolution of closed curve, or by the area, by the here by revolution of the area. Let me take this is area of area, revolution of the area. Which area? A L M B Q A, total area. Okay, by the revolution of area, this is A L M B Q A, this total area. This area is revolved about straight line OX. This is minus sign, then minus sign. Second is volume generated by volume, the difference of these two, because closed curve we are under, generated by revolution of area, by revolution of area A L M B P A. This is A L M B P A, only this area, below area. So subtraction of these two volumes will give us the actual volume of this closed curve revolving around this area. That is the point. What is this area? Let me write it now. Therefore, this area will be given by, let me write here. So the volume of this, therefore volume of revolution of the closed curve, this closed curve A P B, this is Q here, this, sorry, by dash I have taken only this is the closed curve here. So A P B Q A, A P B Q A is equal to this I'm talking about. Now this is within the limits A to B we have taken. Now this is, I have taken this by 2 because length of this closed curve, top point is this. So this is AP, sorry, y2 here. This is y2 square into dx